about gravitational waves, interplay between geometry and physics.
Thanks. Um, Compared to the other talks in the workshop, this is a little bit different in the sense that most talks are focused on some specific topic and go through it in detail. This is more like a broad overview about how geometry and physics come together to describe gravitational waves. I thought that this topic was appropriate for this workshop for several reasons. First is that there's a lot of excitement about gravitational waves seen by detectors and what do they mean in terms of real formalism or geometry, if you like. And secondly, there is also a lot of interest in the particle physics circles, particularly led by Andy Strominger, about some ideas related to null infinity and gravitational waves and such things. So this also makes contact. People might have heard words, and some of them will make sense after after the talk. And finally, the Simons Center is Center for Geometry and Physics. So it was appropriate to talk about geometry and physics in the Simons Center. So the talk has these parts. I'm going to explain all the terms. The first part is null infinity and the BMS group, which is what the arena for describing gravitational waves. The second part is how do you extract these, what you want to call gravitational waves. It is non-trivial. And then you can actually do very nice symplectic geometry of these gravitational waves, and that defines for you the Bondi form momentum, and then some recent developments on open issues. So this preamble, the audience is quite diverse, and therefore I just apologize to experts in the audience. They know most of the things that I'm going to say in the first few transparencies at least. But the notion of gravitational waves is really highly non-trivial in full general relativity. In the linearized theory, people have understood it for a long time, following what we mean by electromagnetic waves in the Maxwell theory. But in gravitational waves, the first problem is that, say, for Maxwell fields in Minkowski spacetime, it is simple to define what you mean by radiation zone. You look at this 1/r behavior in some ways, because we have got a fixed metric. For gravitational waves, we have to define radiation zone and fall off of physical fields using a very space-time geometry whose radiative content is being studied. So boundary conditions in the study of gravitational waves are more subtle than the familiar ones at spatial infinity, because the very presence of gravitational waves introduces some new features which are absent at spatial infinity. And it has to do with what is called the Coulombic aspect, which are present at spatial infinity, but there are also radiative aspects. Now, all this is just a preamble. We're going to see this in detail. And the second thing is that the diffeomorphism invariance of the theory really makes it difficult to know what is a wave. What looks like waves in one coordinate system doesn't look like a wave at all in another coordinate system. There is a famous metric by Levi-Civita discovered already in 1919, which is, they discovered a family of metrics, and one of them is called, Ehlers and Kuhn classified it, and it's called A, B, and C, and so this is the C metric of Levi-Civita. And this metric has a killing vector field, which looks stationary, and therefore for a long time people thought that there are no gravitational waves in this space-time. But to really understand, in another coordinate system, it did look like there was a gravitational waves, and so there was a confusion for a long time. And it took many, many decades to really dispel it precisely. And it turns out that the space-time does have gravitational waves. You can interpret the space-time as being two black holes which are accelerating coming in from infinity. There is some strut in between, so unphysical stress and tensor, if you like, in between them. And then they go out again at infinity. So this is like a spring, and it cannot be compressed beyond some time, and then goes out to infinity. And because you've got these black holes which are doing scattering, there is actually well-defined gravitational waves. So this is the kind of problems that we have. The ridge geometry, there is a ridge geometry that underlies the gravitational waves that are emitted by isolated systems. But the full content of the geometry, I think, is not well known either in the geometric analysis circles or in numerical relativity circles. And so my goal is to explain this interplay between geometry and physics. Oops. Okay. So let me begin by null infinity and asymptotically flat space-time. So for a long time, there was a confusion, as I just said, about the reality of gravitational waves. Already in 1916 to 1918, Einstein wrote a bunch of papers in which he described that if you have linear gravity, and if you have, in other words, Minkowski space and weak field limit of general relativity, and if you have time-changing quadrupole moment, then in fact you have gravitational waves, and they actually carry energy, they have physical quantities, and so on. But then in 1936, he came to the opposite conclusion, and by working with this Einstein-Rosen paper, actually, and he actually suggested that, in fact, in a letter to Bohr, he explicitly said that this finding gravitational waves in the linear theory was misleading because it was just an artifact of linearized theory, and the full general relativity, in fact, gravitational waves do not exist. It turns out that there was a mistake in the analysis, and then it was corrected later. But this really shows why it is so difficult. And finally, starting from the mid-50s to 1980s, the work by Bondi, Sachs, Newman, Penrose, Trautmann, and other people really clarified this structure very much. So again, this is a gentle introduction first. So the physical idea is really that if you start out with a physical space-time, so you say that a physical space-time is actually, oops, it is difficult to control this one. So physical space-time is actually m tilde g tilde. It is said to be asymptotically Minkowski, roughly speaking, if g tilde approaches Minkowski metric as 1 upon r in a specific direction. But the key point up here was that you would like to approach, to leave this, to recede from the sources in the null direction, because the radiation actually goes in this null direction up here. And that specific fashion was spelled out by people like Bondi. And then was made more formal by Penrose, more geometric, and that is what I'm going to use. So in the coordinate system used by Bondi, if you go, in which you use a retarded time u, so t minus r if you like, and so u equal to constant in the surface like that, and you're going out to infinity, then the physical metric, g tilde, goes to Minkowski metric, right? I mean, plus certain terms which fall off like 1 upon r, but the precise, in a precise manner that they spelled out. But what happens is that the presence of gravitational waves adds an unforeseen twist. And this is the key point, which we're going to come back again, that what happens is that there is no longer a canonical Minkowski space that the physical metric approaches. The possible Minkowski spaces, in other words, given a physical metric, it approaches the Minkowski metric plus 1 upon r term of certain form, and it can also approach another Minkowski metric plus 1 upon r terms of the same form, if they differ by what is known as angle-dependent translations. Again, I'm going to explain this notion. So therefore, the asymptotic symmetry group turns out to be not to be a Poincare group. You see, at first you say that if the metric is actually going out as you go out to infinity, it becomes flat metric, then the asymptotic symmetry group should be a Poincare group. But it is not. And this is the reason that, in fact, these boundary conditions are subtle, and we're going to see in greater detail. The subtleties really has to do with gravitational waves. If there are no gravitational waves, then we can reduce the symmetry group to the Poincare group, as we'll see in the talk. So this is what really happens, as I said up here. If there are no gravitational radiation, then the BMS stands for Bondi, Metzner, Sachs. So there is an asymptotic symmetry group is much larger, and that group reduces to the Poincare group. Again, I'm going to explain all these things now. Okay. So first of all, we start with the notion of what is conformal completion. I already had this picture up here. You've got a physical space-time with some sources, and then what you're doing is you are bringing infinity, attaching a boundary to the physical space-time, and this is a conformal completion. The physical metric up here is not well defined at the boundary, but if you conformally rescale it, then it is well defined on the boundary. So physical space-time m tilde g tilde is said to be asymptotically flat if it admits a conformal completion. So where the manifold M has a boundary, so there's a physical space up here and a boundary up here, where this boundary is a manifold, has a given, I didn't write down, right? Oh yeah, no, where the topology of that boundary is S2 cross R, And the conformally rescale metric is just given by omega squared times g tilde AB. Therefore, the omega is a conformal factor. At the boundary, the conformal factor vanishes, but its derivative does not vanish. So if you like, the conformal factor is a good coordinate on the boundary. We can do Taylor expansions around the boundary. And doing the Taylor expansions in the conformally rescale space-time corresponds to 1 upon r expansions in the physical space-time. And finally, the metric G tilde AB, the physical space-time metric, satisfies Einstein's equations, but where the stress energy tensor falls off as you go out to infinity, so that omega to the minus 2, omega is 0 on the boundary, so omega to the minus 2 blows up. That means G tilde AB, the physical stress energy tensor, has to fall off at a certain way that it has to admit a smooth limit to Scri. And as I already said, the topology of Scri is S2 cross R, and it is complete in some technical sense. If people are interested, then I will explain exactly what I mean by completeness. So these conditions actually, just using the Einstein's equations that I have written down with this fall off, they imply, first of all, that Scri is null. These are the Einstein's equations without any cosmological constant. In this case, the Scri is null. And we can always choose the conformal factor just using the freedom that we have, so that Scri is divergence free. So basically, this is the restriction that I'm going to put, that everybody puts, that Scri is S2 cross R. The null normal to Scri, it's a null three-dimensional manifold. So I got ruling of this Scri by this null normal, NA up here. So you can think of a coordinate u going around and coordinate theta and phi going around here. I'm using all kinds of indices, but usually this is meant to be the Penrose's abstract index notation. We don't really need coordinates. They just, occasionally there are coordinates, but most of the time we don't really need to introduce coordinates.
You have the covariant derivatives in 2 different colors. Is that significant?
Yeah. So this was just because I'm talking grad A omega up here to identify with the vector NA. So from now on, this vector NA that I'm talking about is just the covariant, is just the contravariant normal to Scri up here. That's also just identifying the two things. So as a standard, I will work in this conformal frame.
With respect to the rescale metric?
This is all with respect to rescale metric. So no tildes, that means rescale metric up here. So these are the covariant derivatives. So thank you for asking questions. Please ask anytime you need any clarification. Okay. So in addition, the conformal factor, you could go further and ask that the conformal factor be such that not only is Scri divergence free, so this is why it looks like a cylinder, grad A and A is just equal to 0, and this hat just means this equality is holding at Scri. Okay, that's all it means. Right. So, but what you can do is, in addition to that, you can ask that the metric on these round these two spheres where I got should be the unit two-sphere metric, so that the physical space-time metric then just looks like du dr, because Scri is null. R equal to, R is really, I should have put here du omega. It's not R. It is du omega plus d theta squared plus sine squared theta d phi. So this is a typo. This should be omega. So this is the null. These are just the null coordinates up here. And then you see here that the metric on the two-sphere is just a unit two-sphere metric. Now, there is a theorem due to Garrosh which says that if, in fact, the space-time admits a conformal completion, then this conformal completion is unique.
That's the comment?
Yeah.
This theorem of Garrosh is not completely clear. I mean, if you add some conditional geodesic, then it can be easy.
Right. Thank you.
The way it's written.
Yeah. Right. Thank you. And please make such comments because I'm not asleep. And then there is a issue of existence. And now this is important, particularly for this community. See, originally the whole business about Scri was started to describe, stars and black holes which are going around each other emitting gravitational waves. So one is really interested in retarded radiation emitted by sources. But we really don't know any such solutions, or we don't have any hard results showing the existence of such solutions. We do know them in the stationary case. If they're not radiating any gravitational waves, right? In that case, there are many solutions. But in the case, this is all for the case. This framework was developed to describe radiation, And in that case, there are no hard results. So for example, if one could show that Schwarzschild and Kerr are non-linearly stable, then the statement will be, then we'll have some sources, and there will have some weak radiation that is emitted from them, and then we will have such results appear. But for vacuum solutions, of course, there exist results, as you all know, for small data, and this is the non-linear stability of Minkowski space. So in this case, if I go back to the picture that I had up here, there are no sources, but rather the waves just come in from infinity and then go and then are scattering off to infinity. So in this case, we do have a lot of. In this case, there are several theorems, particularly Krustel-Kleinemann, Krustel and Dille, and some work by Friedman, by Helmut Friedrich. So what about asymptotic symmetries? So the statement is that consider now space-times which admit such a completion. And the asymptotic symmetries, the group here was the Bondi, Metzner, Sachs group, and that is called the BMS group. So the idea is the following, as usual. If you want to find a symmetry group, first you have to specify the structure which the symmetry group is going to leave invariant. So this is called the universal structure on Scri, which is shared by all asymptotically Minkowskian space-times that I just described, which satisfy the condition that I just specified. So, for example, the space-time may be stationary, it may have radiation, it doesn't matter what the details of the space-time are. If they satisfy the definition, if they are asymptotically flat, then the statement is that Scri, in all cases, is equipped with some structure. The first is that, as I said before, Scri is S2 cross R. It is null, so the intrinsic metric on Scri is 0 plus plus, and the degenerate direction is precisely this NA. And this condition then turns out to imply that in fact ln of QAB equals 0. So this metric QAB is really dragged along the flow. Therefore, it really is, if you like, a metric which is pulled back from the base space. Let me call the base space S up here. This is the base space, which is really the space of generators, space of these null vector fields up here. That's a two sphere. And so that's what we have. And then, so NA is null normal, QAB is the intrinsic metric with that signature. I already wrote down the second equations. And finally, we still have conformal freedom. And that conformal freedom says that I can make a conformal transformation GAB. Given a conformal completion, so there's already a conformally completed space-time, and I can have G prime AB to be equal to omega squared GAB. But with this condition, the statement is that ln of omega has to be equal to 0 on Scri. And the statement is that how are these Q and N related to each other? So QAB, then Q prime AB and N prime A, this pair is mapped to just omega squared times QAB and omega to the minus 1 times NA. So we got these pairs which are related to each other by these conformal transformations. So I got this equivalence relation up here where omega is nowhere vanishing and ln omega is equal to 0. The BMS group is just a subgroup of the diffeomorphism group on Scri, which preserves this universal structure. So it's a diffeomorphism group. It should preserve the vector field up to a rescaling. That rescaling can only depend on theta and phi, if you like. It's constant here. And the metric has to be then also conformally rescaled, but it's important that there's a precise relation between these powers up here that we are given. Okay. So at the infinitesimal level, at the level of vector fields then, so vector field C is a BMS symmetry. If the lead derivative of the metric is 2 times some function, and that function will also have to satisfy ln of f equal to 0 on Scri. So I get here is a symmetry of lead C of QAB is equal to 2f QAB, and lead C of NA is minus f. So minus f just comes from omega minus 1, and 2 comes from that 2 up there. Now it turns out that if you look at all these vector fields, there is actually a Lie ideal, and this Lie ideal is that of supertranslations. In other words, I can have vector field C, which is just along this vector field NA. So it is going to be, is it what I call it, alpha or beta? Alpha, thank you. Alpha times NA. So CA is just equal to alpha times NA. So we can just consider such vector fields of this type. You can check that they will satisfy this condition if and only if alpha is also lead dragged by this NA up here. And these vector fields, you can show that in fact, if you start with one such vector field and then arbitrary BMS generator, then again you get back another of those vector fields. So that's why this is a Lie ideal, or it's a normal subgroup. Super translations form a normal subgroup of the full BMS group up here. So we got a normal subgroup, which is the subgroup of super translations. We just move up and down the fibers in an angle dependent way. Next, the base space of Sky, which is this S that I talked about, has a topology S2. And therefore, it is a unique conformal structure. And as a result, and we can ask, what is a conformal isometry group? And it is well known that that isometry group is just the Lorentz group. And therefore, if I quotient the BMS group by the supertranslation subgroup, I just get the Lorentz group up here. And therefore, the BMS group has a structure which is really the semi-direct product of the supertranslations with Lorentz. So it is exactly like the Poincare group. Poincare group is a semi-direct product of translations, 4-dimensional subgroup times the Lorentz transformation, Lorentz group up here. Now we've got infinite dimensional freedom because this S is really corresponds to these functions, alpha, which are functions of theta and phi. Yeah, please.
Does the Robinson-Trautmann metric have this property?
Our expert on Robinson-Trautmann is Piotr. He has done a lot of work on Robinson walk. So the statement is that the question is being asked, is the Robinson-Trautmann metric asymptotically flat? Except that it's not complete. It's not. So it satisfies this property, except that the vector field NA is not complete. So it is really just like that.
Okay. So that's the only.
That's right.
That's the only problem.
That's a problem. It's not. I mean, it's not a problem. We can still talk about radiation and such things.
This is how you did
Right. So the statement is that it will not be the BMS group. The Lie algebra is still well defined, but this is not complete, so I cannot move arbitrarily to the
The
future.
geometric structure is it's a real affine line bundle over the two sphere.
Yeah.
Trivial one.
Yeah, trivial.
Of course, it's connected, so there's no other one. And then this group S is actually, you can think of it as the cross sections.
Yeah, you can think of it as cross sections, right? Exactly. You can. So
Just
I mean,
add on
different. Exactly. So you can say that. Yeah. Finally, this was kind of a very non-trivial statement, the result of Ray-Sachs, that even though we got all these things, it also admits a 4-dimensional group of translations. So sitting in this group of super translations, there is in fact a 4-dimensional abelian group of translations. And if we choose the metric Q to be the unit 2-sphere metric, so the boundary frame, then you can say what those translations are. They are just given by functions times NA, and these functions are just linear combination of y0, 0, and ylm. So it is really a linear combination of the first 4 ylms. And therefore, because we got preferred translations, we can talk about the bonding 4 momentum. Because the 4 momentum is always momentum map, so you need a action of a group, and that's a group of translations up here. Okay, so then this is the first part of the talk. We know now that universal, all asymptotically flat space-time have this metric, and then we got this universal structure. Then let me talk about the second part, which has to do with radiative modes. So how is the information of gravitational waves in general relativity encoded at Scry? Well, the universal structure is common to all space-times, stationary as well as radiative. So it serves as a kinematical background, rather like the Minkowski space for Maxwell fields. And radiative information then is encoded in the next order structure, which is not universal. So in the stationary space-time, that structure will be one. In radiative space-time, it will be another. Now, from a geometrical point of view, if you ask, well, I got a metric which is given to me, and I'm looking for a next order structure, what would it be? Well, it is a connection. And indeed, the next order structure is really the connection. And the connection on the conformity rescale metric induces a natural intrinsic connection D on Scry. And this D, of course, kills the metric and kills NA. So if you give me one conformal frame, so you got QAB and NA, then I got a connection D, which kills these things. But because the metric is degenerate, therefore there are infinitely many connections. You don't have a single connection up here. There are infinitely many derivative operators, and each conformal connection of a space-time. If you give me a particular space-time, for example, the Kerr space-time, and I do the conformal connection, then I get a 1 that is coming from the conformal completion of the Kerr space-time. If you give me a radiative space-time, I'll get another connection. The universal structure is the same, but the connections are different. However, from a physical space-time, there is a conformal freedom in the choice of the conformally rescaled metric G that I just wrote down. GAB can go to G prime AB, which is omega squared GAB. And even when omega is equal to 1 on scry, therefore QAB and N don't change. Omega is equal to 1 on scry, but the derivative of omega is not 0 out there. Therefore, the statement is that you actually obtain a bunch of connections from a conformal completion of a physical space-time, and therefore we sort of say, well, what is the difference between, if in fact I perform such a conformal transformation, what happens? I get a connection D prime minus D. The difference between two connections is always a tensor, and this tensor has a very specific form. These indices are just QAB, and this index up here is just N, except that there is an arbitrary function which is sitting out up here. So thus, intrinsically at scry, in any conformal frame, what we really have is an equivalence class of such connections of such derivative operators. In any conformal frame, QAB, NA, just at scry, we have this equivalence class of connections. And this equivalence class represents what you mean by gravitational radiation in full general relativity. So a very beautiful, simple idea, and it actually is right. In the sense that if you now, and this generalizes what happens in non-abelian theories like Yang-Mills theory and so on, the radiative content is all in these connections up here. But now there's a notion of classical vacua, and this is borrowed from Yang-Mills theory. While the equivalence classes at scry, equivalence class of QAB NA as universal, GA, the equivalence class of connection, varies from space-time to another. So you ask, how many such D are there on scry? Well, because each of these D satisfies those compatibility conditions, and any two which are related by, any two of them are therefore related by a tensor of this particular type. And we just saw that the equivalence relation, D bar is equivalent to D, if in fact the sigma tensor up here that I wrote down is a multiple of the metric, and therefore what counts is only the trace-free part of that big sigma, and that is what I have written as, sigma up here. It's just the trace-free part of this big sigma up here. So there are as many such connections as there are tensors little sigma AB, which are symmetric, which are transverse, and which are traceless. In the physics terminology, they represent the two polarization or helicity states or radiative modes of gravitational waves in the full nonlinear general relativity. Now, I ascribe a three-manifold. I got a particular derivative operator on it. I can calculate its curvature, and because it's a three-manifold, there's no wild tensor in it. Therefore, this curvature actually has a very simple form. It is just completely given by a second-rank tensor, SBD, which if you had a metric, which is a regular metric, then this SBD will just be the Ricci tensor minus, in 4 dimensions, 1/4 the metric. But now we don't have non-degenerate metric, so I got this tensor SAB up here. And this S is obtained from here by just lowering the index with the degenerate metric Q that I got up here. So this S has more information than the lowered one. The conformally invariant part of this S up here is called the Bondi-News tensor. So there's a very beautiful construction due to Bob Garrosh, which extracts very nicely the conformally invariant part of this object, and that is then the Bondi-News tensor. So you had heard about News function and such things. That is not quite a geometrically correct description. News tensor is a tensor, the Bondi-News tensor. It's a symmetric, second rank, and transverse, and traceless. Through its curl, that is to say, if I just take the derivative and skew symmetrize on these two indices, then this full tensor S up here defines for me the magnetic part of the Y tensor at the scry, more precisely omega to the -1 times C star. Ascribe the conditions say that the wild tensor itself is 0 of the conformity rescale metric, but omega to the minus 1 times that does not have has a well-defined limit, and this is the magnetic part of the wild tensor. If I should have looked up the notation used in geometric analysis, which is different from Newman-Penrose, but in the Newman-Penrose notation, that star KAB has information about psi 4 naught, psi 3 naught, and imaginary part of psi 2 naught. So this falls like 1 upon r, this is 1 upon r squared, and this is 1 upon r cubed, and that star KAB is that. So given the connection from its curvature, I can get the Bondi-News tensor, and I can obtain these components of the wild tensor up here. If star KAB equal to 0, you can show that the News tensor must also vanish. And so we say that if in fact D is such that star KAB vanishes, then this connection, equivalence class of connection, is called a classical vacuum, following the terminology in Yang-Mills theory. So it is a classical vacuum if in fact its curvature is trivial. Okay. Now the interesting thing is the following, that we just saw that the BMS group has this super translation subgroup. That is to say, it's an infinite dimensional generalization of the Poincare group. How did this happen? Well, there is a one-to-one correspondence between this generalization of this enlargement of the BMS group from the Poincare group and the number of classical vacua that you have. More precisely, denoted by C naught, the collection of classical vacua. This C naught has a structure of an affine space with the following properties. As one would expect, the action of the BMS group on the BMS group B leaves this, it should be leaves this collection, I should have C naught up there, collection C naught invariant. So if I have a classical vacuum and I apply it on by BMS group transformation, I again get a classical vacuum. The curvature was trivial, it remains trivial. Furthermore, each individual vacuum is really left invariant by translation. The four-dimensional translation group we have leaves invariant each of these individual classical vacua whose curvature is trivial. And the quotient of the super translations by translations, this is an infinite dimensional group of the infinite dimensional group of super translation by its four-dimensional subgroup of translation. That acts on this collection again should be C naught simply and transitively. So that, if you like, I mean, they're isomorphic. There's no natural isomorphism. This group up here is abelian, so it's a vector space. D naught is really, the collection of D naught is an affine space. These are the connections up here. But if you choose any one of them as vacuum, as the origin, then the two are naturally isomorphic with each other. So the statement is that there really is a correspondence between this enlargement from translations to super translations and having many of these vacua. The full subgroup of the BMS group that leaves invariant any one classical vacuum, I already said that translation leave it invariant, but the full subgroup of the BMS group that leaves any one classical vacuum is a Poincare subgroup. And the reason why we got all this huge BMS group is because we have to put together these Poincare subgroups. All these Poincare subgroups are the same translation group, but they are different Lorentz groups. And that is what causes this enlargement. Because there is an infinite vacuum degeneracy, there is an enlargement of the Poincare group to the BMS group. If a spacetime has no radiation, then Scri is equipped to the equivalence class D naught of a vacuum. Therefore, I can add this D naught to the structure that should be preserved by the symmetries. If I do that, then the BMS group reduces to the Poincare group. So if there is no radiation, I got Poincare group. However, in general, there is radiation. I don't have a classical vacuum. Even if radiation dies out, then in the future, I got a particular classical vacuum. In the past, I got a different classical vacuum, and that's why I got I cannot get a reduction of the symmetry group. Okay, in the Newman-Penrose language that maybe you are familiar with, each of these D naught provides us with a four parameter family of shear free cross sections on Scri, and the Poincare group, which leaves this D naught invariant, maps these cross sections into each other, and that is how the Poincare reduction takes place. In presence of gravitational radiation, as I already said, the connection is D with non-trivial curvature. It is this that enlarges the Poincare group to the BMS group. Let's understand this a little bit more, because from a physical space-time perspective. In the beginning, we said that, in fact, a physical metric the conditions at null infinity, you can just derive from starting from there, introduce a certain tetrad, certain coordinate systems, and we can show that in fact the metric should actually the metric G hat AB goes to Minkowski metric plus 1 upon R, where 1 upon R terms have some specific form. So as I said in the very beginning, so one would normally think that therefore the symmetric group should be the Poincare group of eta, but it is not. And why does this happen from a physical space-time perspective? The reason is because we can find distinct Minkowski metric eta prime AB such that G hat AB, the physical metric, is also given by eta prime AB plus 1 upon O upon R prime, and these terms again have the required specific form. Asymptotically, the two Minkowski metrics eta AB and eta prime AB will differ by an angle-dependent translation. That is to say, T prime will be equal to T plus some function of theta and phi. And for example, in this particular example, X and Y and Z don't change. And this is precisely, if I look at what this transformation does to Scra, it is precisely a supertranslation. So this is an example of a supertranslation. So therefore, the point is that the Poincare group defined by eta AB is a subgroup of the diffeomorphism group, which is distinct subgroup from the Poincare group that is defined by eta prime AB. Roughly speaking, the BAMS group is a union of all the Poincare groups of Minkowski metrics, eta, eta prime, eta double prime, etc., to which the physical metrics approach in the desired fashion. So in particular, the Poincare groups of eta and eta prime AB, in particular, the Poincare groups of eta and eta prime AB are subgroups of the BAMS group. And furthermore, they share the same four-dimensional translations, but their Lorentz subgroups are not shared. They are mapped from one to another by this particular supertranslation. There's also a lot of discussion about gravitational memory effect, soft gravitons, and so on, and that all is really understood in terms of this classical vacuum at D naught. I mean, if you have got a pulse of gravitational wave coming in, going out up here, right? We had this in a picture. A pulse of gravitational waves which come out, and supposing there was space-time was kind of stationary here, space-time again becomes stationary, then the D naught here is different from D naught here. If you like, the adapted Minkowski metric to the leading order is different from different from the adapted Minkowski metric, and therefore, in fact, the detector will undergo a certain displacement, and that displacement is really completely governed by the supertranslation that I talked about just a while ago. Okay, so this can be all understood in terms of this vacuum degeneracy. So now I've done with the first two longer parts of the talk, and now I would like to talk about the symplectic geometry of radiative modes and the Bond-Diffour momentum. The third part is symplectic geometry, and the first three parts are quite old work, most of them, and they are reviewed in this paper in the Beery Yao volume, Surveys in Differential Geometry. So let me start now with the third part up here, the phase space of radiative modes. So, of course, the phase space of radiative modes is just constructed by putting together all radiative modes, and that is to say, is a space of all gravitational connections D on Scri whose curvature falls off, the K star AB falls off at the two ends. So here is Scri, and I want the curvature to fall off at the two ends, otherwise the total energy that will be emitted will be infinite. So I got this connection D such that its curvature falls off as U goes to infinity and U goes to minus infinity. As U goes to infinity, we go to this point called I naught, and as U goes to minus infinity, I go to the spatial infinity point up here. So that's what we are asking, I plus, and the other way. Thank you. I knew that something was wrong. I naught and I plus. Thank you. So the symplectic structure on this space is an affine space, and on that there is a symplectic structure. So it's a two form. So the tangent vectors at any point D is given by delta D, is, as we just saw, difference between two connections is a symmetric second rank transverse traceless tensor, sigma AB. And therefore the tangent vectors are symmetric transverse traceless tensor fields. And then the symplectic structure is just given by sigma ln of sigma prime. So I got two tangent vectors, sigma and sigma prime, minus the other way around. And formally, this omega is derived starting from the covariant phase space of vacuum solutions of G tilde AB. It will be very nice to make this very completely rigorous, for example, in the framework of Kleinman or Crucial-Delay, etc. It will be nice to make this completely formal, completely rigorous. Action of the BMS group on Scri preserves omega. So we got a symplectic space. I got a symmetry group. And the first question one was going to ask is, does the symmetry group preserve my symplectic structure? And the answer is yes, it preserves. And therefore, associated with every symmetry, BMS symmetry, we really have a Hamiltonian function or a momentum map, if you like. Namely, the Hamiltonian which generates the Hamiltonian vector field corresponding to the displacements which are induced by the action of the diffeomorphism C on these connections D up here. That is just given by the Bondi-News tensor times something. And that something is very simple. Each of these connections D up here is completely specified by giving the action of D on a vector field L, one form L, such that which is kind of transverse to n, L dot n is equal to 0. Basically because of this condition, namely because of the condition that dA of QAB equal to 0, dA of NB equal to 0, because of this condition, the only freedom, if I take any vector which is really tangential or one form, which is really pulled back from here, up here, one form which is pulled back from here, then the action of the derivative operator is exactly the same, doesn't change. So that D is completely determined by the action on L, where LA NA is equal to 1 at Scri. So just one of these one form. And then the extra term is the simplest thing that you can imagine. It is just you just take the lead derivative of this L, and then take the derivative operator, and the other way around. So it's just the commutator of the lead derivative with the derivative operator. So in other words, this is exactly what it can be, right? I mean, what is the action of a vector field on a connection? That would be the action of the connection. So it's again very, very pretty and just turns out to be the right answer. And so in particular, if you take a super translation, so alpha is a function of theta phi, then the flux is given by the formula that I had on the last transparency up here. You can evaluate what that is, and that is very simple, and that is just given by, again, alpha times n plus dA dB alpha, so second derivative of alpha. Again, those of you who might read the literature from quantum theory, this part is called, which is quadratic part up here, is called the hard part of this Hamiltonian, and the part which is linear in the news is called the soft part. If you have a BMS translation, then in fact, as I said, in the Bondi frame, alpha is just one of the first 4 YLMs, therefore dA dB alpha is just proportional to the metric, and that, since NAB is traceless, that term just goes away, we don't have anything left. And therefore the statement is that for translations, only the quadratic part, the hard part, that survives up here. And now we can see that for the translations, we see that if it is a time translation, then this function alpha up here, if it is a time translation, it is a positive function, and then the Hamiltonian is just NAB, so it's just a square of NAB, and so gravitational waves carry positive energy. The flux across any portion of Scri is just given by that formula restricted to that portion of Scri. Now, fluxes, these flux functions that were given, so it's a flux of, this Hamiltonian is a flux of energy or momentum carried by gravitational waves across Scri. Fluxes are functions on the radiative phase space. As one would expect, the BMS momenta themselves require Coulombic information that is not in the radiative modes. It requires information about real part of psi 2 naught, which is not in the, so the Coulombic information is in the real part of psi 2 naught. So this again is a quantity which the Newman-Penrose invariant which falls like 1 upon r cube. And that is not contained in the radiative modes. But in any given space-time, we know what the flux is across any such region, so we can just integrate the flux. And then we get a formula that the total flow momentum associated with any cross-section of Scri is just given by this, The time derivative of this is the flux that we talked about here. Therefore, if I evaluate this quantity on 2 cross section and take the difference is precisely the quantity that I got up here. So you just integrate that equation to obtain this BMS, this bond difference momentum. And this psi 2 naught carries the Coulombic information. Now, positive energy theorem tells us that this quantity is positive if, in fact, matter satisfies the standard energy condition. And this is a stronger result than the positivity of the energy at I0. So for a space like infinity, most of the talks were talking about this. So space like infinity, we got surface like that, and we're talking about energy up here. And but here the statement is that is the energy positive? If in fact gravitational waves could carry more energy than there was in the mass, ADM mass, then the Bondi energy would be negative, and the positive energy tells us that that cannot happen. Okay, so this takes me to the last part, which has to do with recent developments on open issues. So what we have seen so far is that we have got a nice definition of asymptotic flatness. That tells us what the symmetry group is. That symmetry group interacts with the radiative phase space of radiative modes in a very natural manner, and that gives us the physical notions of energy, momentum, and waveforms. The waveforms refers to, for example, the Bondi news, what happens to the Bondi news up here, or if you like, to what the radiative connection is doing. So far, we have focused only on Scribe+ for the following reason. To study gravitational waves emitted by isolated systems, so if you are really interested just in this diagram that I have been drawing, that I got some object radiating gravitational waves, and I got Scribe+ and Scribe-. So I'm only interested in that. Then we want to say that there is no radiation incoming. And this condition is best imposed on Scribe-. So what we are asking is that the connection on Scribe-, this D on Scribe-, should be a classical vacuum. Should just be a classical vacuum up here. That just says that there is no incoming radiation up here. And once it is a classical vacuum, then you don't, all this rich structure trivializes. You don't have to, there's no flux of radiation. We don't have the phase space of radiative modes, nothing. And that is why I focused on Scribe+ and not on Scribe-. But now we can ask the following question. From a mathematical perspective, it is also of interest to study purely radiative classical solutions, as was done in these various papers by Krustulu Kleinemann, Crucial and Dele, and Friedrich. So I can just consider waves coming in from Scribe- and going out to Scribe+. Right? Going out to Scribe+ up here. So in this case, then the D here is not going to be a classical, vacuum. It's going to be dynamical up here. So in this case now, we can ask, is there some nice relations between what happens on Scribe- and Scribe+? So this is, for example, the sector that was studied by these people. Therefore, we have got non-trivial radiative modes on Scribe- that I just said. And there is also a rich framework therefore at Scribe-. And now the question is if there is a relation between invariantly constructed quantities here and quantities up here. Now in Minkowski space-time, if this were a Minkowski space-time, just for a minute, assuming it's Minkowski space-time, then every null geodesic up here, inextendable null geodesic, has an endpoint on Scribe- and Scribe+. Therefore, there is a natural isomorphism between Scribe- and Scribe+. And we can use this, for example, to analyze the S metrics for the Maxwell field. And one finds that not only is the energy momentum conserved, but also the analogs of the supermomentum that I wrote down, the total flux of supermomentum here is equal to the total flux of supermomentum up here. And that is not a very profound fact. That just happens because the S matrix is trivial. So the S matrix is really, once you formulate a problem, you see that the S matrix is identity, and therefore all the constant quantities here will be the same as the constant quantities there. But in nonlinear general relativity, the canonical map from Scribe- to Scribe+ may not exist because you may not have these geodesics, giving us a nice correspondence between them. But one can still ask for conservation laws. Does the flux of supermomentum across Scribe- equal that of Scribe+? Then I don't need to know which point here corresponds to which point. I just calculate the flux here and a flux here. But to do this, we still need to know what I mean by the same super translation here on Sky plus as on Sky minus, because super momentum is the generator of super translation here and a super translation here. So compare, I need to know what I mean by the same super translation. So basically here, I just introduced a notation, plus minus refers to Sky plus and minus. So I got these two super translations. The flux is just given by this. And to ask if there is a relation between what is happening on Sky minus and what is happening on Sky plus, we need to know how do I, given theta phi here, alpha of theta phi here, what is alpha of theta phi here up here. Now, if you ask not only that you have got null infinity, but also spatial infinity in a precise manner, which is called spacetimes which are asymptotically flat at spatial null infinity, asymptotic, so it's called afancy, and it was invented to say that these spacetimes are not very fancy. They are very boring straightforward spacetime. So for this afancy spacetime, so the precise definition up here, then the statement is that the structure at I0 is such that we can actually set up a mapping between generators here and generators here, and it turns out to be sufficient to talk about what I mean by the same super translation on Sky plus as on Sky minus. So in a fancy spacetimes, the path limit of Bondifo momentum on Sky plus and Sky minus is the same. So in the fancy spacetime, I can look at the Bondifo momentum up here and take the path limit. That path limit turns out to be the ADM for momentum. I can take the future limit of the Bondifo momentum. I'm talking about for momentum, not fluxes. And then that is again going to be just the ADM for momentum. Therefore, the path limit here is the same as the future limit here. Therefore, if I had such a situation, that Minkowski spacetime, gravitational waves coming in, gravitational waves going out up here. In such a situation, what we can ask is the following. In such a situation, the Bondifo momentum in the distant future is 0. Bondifo momentum here is 0. So the ADM momentum up here, if you like, is really the flux of the energy momentum across Sky and flux of energy momentum across Sky minus. And what this result shows is that the flux of energy momentum across Sky minus is equal to the flux of energy momentum Sky plus. So we got quite nice conservation law in full non-linear general relativity. But what about supermomentum? Is there an infinite number of conservation laws in the scattering of, for example, sufficiently weak gravitational waves, but in full nonlinear general relativity? And the formal arguments, this is the interesting interplay, formal arguments from perturbative quantum gravity, which are based on so-called Weinberg-Soft theorem, that have been used to propose that in such a fancy space-time, there are indeed such conservation laws. The Bondi supermomentum on Sky minus must be equal to the Bondi supermomentum on Sky plus. But these are formal arguments in which are infinite quantities, ill-defined quantities. One makes manipulations in quantum theory between these ill-defined quantities. And so one can ask, well, forget about quantum theory. Take this as an indication, and I can ask, in general relativity by itself, are there any conservation laws that I can talk about? And it has been argued that one can. So this is the various arguments that are put forward by the Harvard group. But if you do a closer examination of it, you find that in fact they are restricting themselves to a situation in which the total flux of Bondifo momentum, total flux of supermomentum here and is 0. The supermomentum here is 0, and therefore we are just showing that there is a conservation law which just says 0 is equal to 0. It's not much of a conservation law, right? I mean, it's like taking a spherically symmetric configuration and say that I got a conservation law of angular momentum. Yeah, because it was 0 in the beginning, it's always 0, so it's not very profound. And so the question is, but the argument is too restrictive, but the question is still very interesting. Is it true that in full nonlinear general relativity, we have non-trivial conservation laws for supermomentum? And the last part I would talk about is gravitational waves in physical cosmology. Yeah.
Not settled yet?
No, it's not settled yet. And we can discuss later. It's not trivial to settle it, but okay. The second thing is about gravitational waves in physical cosmology. Well, while LIGO collaboration has seen gravitational waves produced by binary black hole collisions, cosmologists are also interested in primordial gravitational waves that have always been around. And in fact, it was announced that these have been these were discovered before LIGO, but turned out that that was not a reliable announcement. So the announcement was incorrect. So since the universe is not asymptotically flat, although we are going to hear a little bit more from Beatrice about what one could do in terms of scry in such cases, but still we cannot really use this Bondi framework, that Bondi et al. Framework that I talked about, to describe gravitational waves. So therefore, they do something else. First of all, so far at least, this is really discussed in perturbative treatments. So I got some cosmological background, and you do weak field perturbations, first order perturbations or second order perturbations around them. And second, to talk about modes, they do a transverse traceless decomposition. So let me say what this is in using a familiar example of Minkowski spacetime. I could do the cosmological spacetime, but for the conceptual reason, there's no new content, but I will have to use more notation. So I'll just use Minkowski spacetime and remind you what transverse traceless mode mean. So in Minkowski spacetime, you can consider spatial metrics. So you take a foliation of spacetime by planes, and the spatial metric on a plane is just QAB, and the derivative operator of that metric, spatial derivative operator, is just this D in Minkowski spacetime. So I'm looking at this planes up here in Minkowski spacetime, and I can look at this metric up here and the derivative operator here. Then we can do a certain decomposition, and we can decompose the full perturbation into two scalar modes. H and S are functions. There is a vector which is transverse, and the remaining part is transverse traceless. So the transverse traceless modes are the ones which are supposed to represent the weak field in this limit, in the weak field limit, the gravitational waves. So they just satisfy HAB. I think everybody knows this, but let me write it down. Is equal to 0, and HAB transverse traceless times metric is equal to 0. And that transverse because transverse traceless, so in particular HAB times TB equal to 0 on the Interplay. So they are just spatial tensors that transverse also in that sense. However, the point is that, and then for example, the expression for how much energy they carry can be expressed in terms of time and space derivatives of this transverse traceless mode. But the extraction of this transverse traceless mode, as you all know, from HAB is a highly non-local operation. If you just tell me HAB in this room, I don't know what its transverse traceless part is. I mean, the simplest way is to do the Fourier decomposition, and then in Fourier space it becomes local, but that decomposition is non-local. Or if you like, in order to get HAB TT from HAB, I have to use inverse powers of Laplacian operators all over the place, and that introduces non-locality. So at first it looks very weird, right? That on the one hand there is a formula for linearized gravitational waves, which is very, very non-local on each of the slices up here. On the other hand, I just told you that on scry, in full theory even, the gravitational waves are given kind of locally by this connection up here. If you give me some point up here, then I can just look at or some neighborhood here, then I'll be able to tell you what D is. So, and furthermore, the expression of the gravitational energy carried by gravitational waves, also in the linearized theory, is really, there is no non-locality. So there seems to be some tension. But it turns out that this tension does disappear if you look at the limit as this HAB-TT. So on each of these constant time slice, this is very non-local. But when you go to scry in this limit, very beautifully, in fact, it becomes local. And in fact, this HAB-TT just becomes the linearized D. In other words, if you like, first order variation in this D. So there is a very nice, everything works very well, that this tension is resolved. But for this, the fact that scry is null really plays a very critical role. In particular, if scry were space-like, then this would not hold. So let me just finish with this last remarks about the de Sitter versus Minkowski spacetime. So here was the Minkowski spacetime. These were time constant surfaces. These are the Killing vector fields d by dt whose orbits are like that. In a cosmological de Sitter spacetime, the situation is the following. First of all, let's just consider de Sitter spacetime. The topology of scry is S3. And then the statement is that in this S3 spacetime, scry minus and scry plus turns out to be space-like. They are not null, but they are space-like. Furthermore, there are cosmological horizons. And the time-like Killing vector field up here It's time-like in this region, time-like in this region, but it's space-like near sky. Space-like near sky. So here, when we talk about energy, for example, energy of a Maxwell field in Minkowski space-time, I take a stress-area tensor and I plug it with the time-like time translation and integrate it over here. Since the energy condition is satisfied, I get integrand is positive, so energy is positive. Here, if I were to take a slice like that, then the Killing vector field is space-like, so the energy would be negative. And in fact, can be arbitrarily negative. So in de Sitter space-time, the energy can be negative. Now, when people talk about cosmological de Sitter space-time, they don't mean with the S3 topology. In really cosmology, where they're not talking about isolated systems, but they're just talking about primordial radiation. In the past, you got a Big Bang. In the future, we got Scry up here. And one is just looking at this portion up here. If you like, the Big Bang is somewhere here. So one is just looking at the future portion up here. And then the topology of Scry, I0 is not included. So I'm removing one point from S3, so the topology is R3. If you have an isolated systems, then I have to remove this point as well as this point, and the topology of Scry is S2 cross R. So as we just saw, even for Maxwell field, the energy that can be electromagnetic waves can carry negative energy because the Killing vector field is not time-like. So for example, on this horizon, the Killing vector field is future-directed. On this horizon, the Killing vector field is past-directed. Therefore, waves coming in from here will have, say, positive energy, and waves coming in here would have negative energy. But it turns out that if I had a time-changing electric dipole moment, or in the linearized theory, a time-changing quadrupole moment, then the energy that you get at Scry is always positive. The reason for that is that we are always looking for retarded solutions, and when we are looking for retarded solutions, there is no flux coming in from here. So I can just compute the energy here. Here the Killing vector field is future-directed null, therefore the energy is actually positive, and the energy here is equal to the energy here. So even though arbitrarily negative energy is allowed, it is actually never realized. So the last slide, I just want to summarize what is happening up here. In cosmological de Sitter space-time, in the linearized approximation, the radiative modes as well as the bond-dim news at Scry are now obtained through a transverse traceless decomposition. And in contrast to asymptotically flat case, the extraction is now highly non-local. So this is an open, very interesting issue, namely in full nonlinear general relativity with a positive cosmological constant, we have a host of interesting challenges at the interface of physics, geometry, and analysis. I think the broad picture is clear, but there are certain still many details that are still being worked out. And the theory with the cosmological constant, positive cosmological constant, will differ from the Bondi-Sachs theory, and in particular, the radiative modes of the gravitational waves and the analog of the Bondi news will be extracted in a non-local manner from natural geometric fields at Scry plus. Positive energy theorem will introduce new global aspects because as even in the linearized theory, we had to put this no incoming radiation up here. We'll have to put some extra information, not just analysis at Scry, to ensure that the total energy carried by gravitational waves as well as the analog of the Bondi moment energy is actually positive. So this does provide many exciting challenges, I think, to the whole community. So summary. The summary is basically the following. For asymptotically flat space-time, there is an elegant geometric framework to describe gravitational waves. It combines conformal techniques and sympathetic geometry to express physical notions of radiative modes, asymptotic symmetries, energy and momentum fluxes carried by gravitational waves, and the Bondi energy, the energy that is left over at a retarded instant of time for allowing for the gravitational waves to carry away some energy starting from the ADM for momentum. The detailed conversion of these ripples in geometry, right? That is what the gravitational waves are. But we actually take these ripples and at Scry, we can quantify them in terms of these connections and the Bondi news tensor. And these give you waveforms that you can compute if you have some sources numerically, but you can compute. And to me, it is very thrilling that these waveforms were what was seen by LIGO. Right? I mean, I think this is a very sublime example of coming together of geometry and physics. So interesting problems remain. In particular, is there an interesting tower of conservation laws in scattering of gravitational waves? Are there rigorous existence theorems that incorporate gravitational waves produced by sources as opposed to vacuum solutions in which waves come in from infinity and scatter off to infinity? Is there a satisfactory treatment of angular momentum carried by gravitational waves? Because of time, I did not really go into this topic, but there are some very interesting things that come up from electromagnetic examples that to really allow for realistic sources, one has to remove the condition that the boundary condition at sky, that the star k goes to 0, these quantities go to 0 as you go to sky I plus and I 0. But you just have to ask a weakened condition that the News tensor goes to 0. That requires a revision of the whole framework, and that has not been done. And finally, as I just said, the extension to incorporate cosmological constant offers host of interesting problems at the interface of geometry, analysis, and mathematical physics. Thank you.
Okay, we have time for your questions. Very wide-ranging talk. So
Yeah.
So there was this discussion about BMS groups on black hole horizons. Are there any of this universal structure gravitational connection? Any of this theory still hold true in this context?
Right. So, I mean, the analogy is very weak. I mean, it is not a very strong analogy. It's a mathematical analogy, and it's not okay. So it's not that the BMS group that comes up there is really a subgroup of the diffeomorphism group on the horizon, and so it's more that there are quantities you can define at horizon, which are analogous to the supermomenta, for example, at sky. And now, the first one has to, I think, for me to really do any work in it, I have to first understand it much better than I do now. But there is a potentiality. Basically, on the horizon, you can define certain multiple moments. And these multiple moments correspond to really supermomenta out of sky. So there could be a relation between how the horizon loses its hair, or if you like, the multiple moment structure, and finally becomes curved. So there can be a relation between these and what supermomentum approaches the sky. Now, this is something that a whole bunch of us are looking at because it's also of direct interest to LIGO, because it will tell us something about the waveforms, that there is a correlation between dynamics of the horizon. So we got say, for example, just let's look at collapsing stars or binary black holes, and the statement is that the star is wiggling. No, we need a horizon side. So the statement basically is that you got a horizon. So there's first of all dynamical horizon, which becomes isolated and therefore null here. It is space-like here, and this is sky. This is sky plus. This is I0. This is the horizon.
I plus at the top.
I don't know what's my problem. Yeah, I plus up here, and then the statement is that it is probably true that the multiple moments here agree with, so there's a radiation coming out here. There is radiation up here in this region up here. There's radiation in this region up here. And it is actually true that the multiple moments in future here agree with the supermomenta here. So that is a nice correspondence. There are conjectures that there is a correlation between what falls into this horizon and what goes out into it. At first, it looks very far-fetched, but in fact, I think that there is some truth to it, because both these waves actually are coming in from just outside the horizon in this so-called angular momentum potential well. So things are falling in, things are going out, and they are correlated because they are the same course. This is not something I can prove mathematically, but on the other hand, numerical simulations do indicate that there is a strong correlation between this and this. And therefore, in that sense, then, there will be a strong correlation between what is happening at infinity and what is happening falling into the black hole. The mechanism by which a black hole hair is the razor, so to say, removes a black hole here, is reflected on what is happening at Scri. So that is a kind of possibility that is being looked at much more clearly, much more seriously.
But following this question, with cosmological concept, the current observation actually happened at cosmological horizon. And so what kind of structure can you say?
Right. So the current observations are inside the cosmological horizon, but they believe that so let me just draw the picture. So for example, you may have some space-time like that, and you got some source doing something. So this is Scri plus, this is I plus, I 0. And then, as you said, the cosmological horizon could be here somewhere. Right? Cosmological horizon is here. So the current, so the statement is basically that we are somewhere here. The waves are coming in within the cosmological horizon. But the idea up here is that with respect to the source, we'll be able to see further and further sources. So we might be here somewhere, and we'll be able to still receive radiation coming from here. So the third generation of detectors people are building is supposed to be able to get a reach so that one would be able to receive gravitational waves even from across the cosmological horizon.
Is there any mathematical description about the radiation?
No, there's no. I mean, so that structure, that mathematical description is a structure at the Scri up here. And yes, and as I said, that the broad picture is clear, much clearer than a year ago when I gave a talk at Columbia, but is much clearer. But it's not finished because basically there are a couple of possibilities, and I don't know which one of them is quote unquote right, satisfies all the criteria. So we have to check this out. And there is also possibility of actually defining radiation here, but this has always a problem that in a general space-time, do we know that this past horizon is long enough to actually intersect the future horizon of this point up here and of I minus up here? And I don't control that at all, but one might just assume it and then develop some. So here also, there are the formula for gravitational waves up here, and this work is not finished, but I think broad picture is now basically. So long answer.
Any other quick question?
Any other questions that can be answered quickly?
Yeah, that's right. That's what I'm glad you responded. Okay, well, we'll resume at 11:30. Let's thank everyone.